This conference will now be recorded.
Hello everyone. We'll start with chemical properties of amine, and after that there will be some problems and also the different types of amines. I mean primary, secondary, tertiary, how we can separate them by using some chemical reaction, and also some distinction test. All this will be discussed. And if there is time permits, then aromatic amine, that is a different types of amine where aromatic ring is attached to NH2, that will be also discussed. The first reaction under chemical properties of amine, alkylation. Now when I'm saying alkylation, that means some alkyl group will be added, and the hydrogen that is present in amine, that hydrogen will be replaced by some alkyl group. That is why the reaction is called alkylation. So if it is primary amine, for example, the amine that you are seeing here, this is primary amine because with nitrogen we have two hydrogen. And we are using alkyl halide. Which alkyl halide we have taken? Methyl bromide. So the hydrogen of NH2 group, it is replaced by methyl group, and now we have methyl substituted amine, and this is 2-degree amine because only one hydrogen attached to nitrogen. If we take 2 methyl bromide for 1 mole of RNH2, now it will be converted to 3-degree amine because now we have replaced both the hydrogen with methyl group. Similarly, now if we take 3 moles of methyl bromide per mole of RNH2, there will be formation of quaternary ammonium salt because 3 methyl groups, you can maximum replace 2 hydrogen with 2 methyl, and then it will be having structure like this. But further reaction if it is occurring, that means now it is attacking the alkyl carbon and Br is removed. But nitrogen maximum valency is 3, but now it is having valency 4. That means it will be now positively charged. So that is why it is ammonium salt, and the positive charge is balanced by this counter ion, which is bromide ion. So depending on the requirement, what you want to make, you may want to make 2-degree, 3-degree or quaternary ammonium salt, you have to take the number of moles of alkyl halide accordingly. Fine. So this is alkylation. Next is acylation. Just like alkylation, now we will insert acetyl group. So that is why the name is changed from alkylation. Now it is acylation. Aliphatic primary amine and secondary amine, they can react with acetyl chloride, or another reagent also you can use for this purpose, which is acetic anhydride. And you have to do this reaction in presence of pyridine, which is basically base. Fine. And what we are getting product? N-alkyl acetamide. So see the reaction. This is the general form. Any acid chloride you can take, R prime COCl. This R prime, it may be any alkyl group or it may be any aromatic ring, benzene ring. That is also possible. This primary amine, one of the hydrogen now replaced by this group. So that is why it is substituted amide, because amide group is NH, C double bond O, and both sides there may be any group. But this fragment must be present. I mean NHCO must be present. So here you can see NHCO is present. So final product is substituted amide. In the previous reaction, after reaction, you are again getting amine. But in this reaction, as C double bond O is now attached with NH, so the group itself is changed. Now the product is amide. Starting material amine, and here byproduct is HCl because one of these H, which is basically replaced, that H will be now connected with Cl, and this HCl is acidic. So that is the reason we are using some base, because if this side product is consumed by pyridine base, reaction will be, that is equilibrium will be shifted from left hand side to right hand side. So more product we can get. Now if we are using, that is the reaction, if it is carried in presence of a base which is stronger than amine, then what will happen? It will remove HCl so formed. So equilibrium will be shifted from left hand side to right hand side. Fine. Because concentration of side product is reduced in presence of pyridine. So this is the acylation. Now some examples of acylation also we will see. This is ethylamine because ethyl group is attached to NH2. In this case, R prime group is methyl, and now the name is acetyl chloride. In the previous case, when you are using the general formula, now the name is acid chloride. But now when you are using CH3 in place of R prime, now the name is changed to acetyl chloride. Pyridine is there, heat is there, H is replaced by COCH3 group. Okay, so that is why the name N-acetyl ethylamine, or you can say N-ethyl acetamide. So both names are actually correct. So N-ethyl acetamide means we are considering as if this group is attached to N, so that is why capital N ethyl. But if you are considering that COCH3 group is attached to N, then you can also write it as N-acetyl, as if it is derivative of ethylamine. Now if it is product P, now P you can consider as if it is now starting material, it is reacting with another mole of acetyl chloride. Now this H will also be replaced by another COCH3. So now there are total 2 COCH3 group attached to N. Maximum limit is reached, and you cannot have any, that is extra COCH3 cannot be added. That is a maximum limit. So this is 2 degree amine. It is actually not amine, sorry, it is amide, because you have NHCO group. But in this case, it is 1 degree amine. Another example, now we have started with methylamine or methenamine and benzoyl chloride. So now the R prime group is benzene ring and the name is benzoyl chloride, or you can also write it like this, PHCOCl. Remember, benzyl and benzoyl both are not same. Benzyl, when I am saying, it is actually PHCH2, then Cl, that is benzyl chloride. But when I am saying benzoyl, ZOYL, now it is PHCOCl. And here CO's pH group is now inserted by replacing one hydrogen of NH2 group. HCl is produced as byproduct which will be consumed by base. Mostly pyridine is taken. After acylation, the third reaction is reaction with nitrous acid. Nitrous acid is HNO2. 3 different types of amines, I mean 1 degree, 2 degree, 3 degree. They react with nitrous acid and different types of observation will be there. One important thing, here we do not use HNO2 directly because this molecule is not very stable. So to make this in the reaction medium, we take sodium nitrite HCl. So when you mix these two reagents, in situ HNO2 produced. How produced? This Na is replaced by H. So now it is HNO2. This HNO2 you can write in this way, HO single bond N double bond O. When it is primary amine, you get this type of cation. And if this part is removed in the form of nitrogen molecule, this is nothing but nitrogen molecule. Now you are getting cation. So primary amine structure RNH2. Which cation you are getting? You are getting R plus. If it is 2 degree amine, look at the structure. Now only one hydrogen. Then in presence of HNO2, there will be formation of this type of compound, R2N and N double bond O, nitroso group is attached. If it is tertiary amine, there is actually no reaction, but still if you consider as if this lone pair is capturing this H, because that is a acidic hydrogen, then it will be forming R3NH plus. This plus charge is basically over nitrogen like this, and this positive charge can be balanced by rest of the part, which is the anionic part. Fine, but this is just I mean as the proton capture reaction. This is actually not a reaction, so we cannot say that tertiary amine there is some reaction with HNO. This is simply the attack of lone pair over nitrogen. It is capturing the H and rest of the part is as counter ion ONO. So different types of observation we can get depending on whether you have taken 1 degree, 2 degree or 3 degree amine. So when this primary amine we get alkyl diazonium salt. So this is actually alkyl diazonium salt. Diazonium salt we use when there is N2 plus. So this is N2 plus. When the secondary amine, now what we get? We get N-nitrosoamine. So this group is nitroso, which is attached with N. So that is why it is N-nitrosoamine. This is yellow oily liquid, not soluble in water. This reaction is also known as Lieberman's nitroso test. So by doing this test, because you are getting some specific observation, so that is why you can use this reaction to identify whether there is any secondary amine present or not. And this is Lieberman's nitroso test, because other amines you will not get this type of observation. I mean the yellow oily liquid, that you will not get. And when it is tertiary amine, then aliphatic tertiary amine reacts with nitrous acid. It forms trialkyl ammonium nitrite salt. So it is salt because there is cationic part, anionic part, and as it is salt, that is why it is soluble in water. R3NH plus cationic part, this is the anionic part, ONO minus. Now as they are behaving differently, so look at this 1 degree amine. Now detail, that is if we focus on 1 degree amine, in presence of HNO2, this is HNO2, this type of alkyl diazonium salt, it is produced, that we have already seen in the last slide. Now the next step is very fast. This bond will be broken because in this case a very stable molecule, which is nitrogen molecule. Nitrogen molecule is very stable because there are triple bond between two nitrogen atoms, and to break triple bond is not so easy. So N2 is very stable, and as N2 is very stable, it can be easily removed from R and you can get this cation. So cation cannot remain in this way for long. If you treat it now with water, you can get alcohol. If there is removal of proton from this R plus, suppose if the proton is like this, CH3, CH2 plus, ethyl cation, then one of the hydrogen, if it is removed from this carbon, what you will get? You will get CH2 double bond CH2, which is neutral. So removal of H plus, you can get alkene. This is alkene, CC double bond. And if you have some nucleophile like Cl minus, it can attack and you are getting RCl. So this is the fate of R plus, and that depends on what you are using. H2O, alcohol. If it is removal of H plus, then it is alkene. So in this case, you can use some base and attack of Cl minus. We are getting alkyl halide. So different types of products we can get. If it is 2 degree amine, see this is 2 degree amine because with nitrogen we have only one hydrogen, one methyl group, one pH ring. So for 2 degree we have seen yellow oil, which is basically because of this N-nitroso compound. So with nitrogen, nitroso group is attached. It is N-nitroso methyl phenyl amine. This is yellow oil. Another 1 degree amine. So in presence of NaNO2 HCl, this will be produced. We do not use it directly. Now first there is unstable formation of R plus. Sorry, it is not R plus, it is neutral R. I am trying to write this structure. So this is actually C2H5N2 plus, and counter ion you can write as if it is Cl minus, which is coming from HCl. So C2H5N2 plus, which is alkyl diazonium salt, it is not very stable because immediately N2 is removed. And as you are using water, remember according to this observation, the first one, when you treat alkyl diazonium salt with water, finally you end up with alcohol. So that is why here we are getting ethanol, which is the final product. Number 4 reaction, carbyl amine reaction. Now this reaction is only for primary amine. The previous reactions you have seen, we have used all the amines, but now this reaction, it is only for 1 degree amine. In this case, what we use obviously primary amine, then chloroform and alcoholic KOH, not aqueous KOH, alcoholic. And what we get? We get alkyl isocyanide. Isocyanide means NC. Cyanide is Cl. Isocyanide is NC. So here alkyl group, it is attached with nitrogen, not carbon. So that is why it is different. It is not RCN, it is RNC. And that is actually called carbylamine. Now, why this test can be used for identification of primary amine, which is mentioned in the second point? Because there is a specific unpleasant smell, and because of this specific unpleasant smell, it proves that 1 degree amine is present. Because this type of compound, which is actually responsible for unpleasant odor, that you can get only from primary, not secondary or tertiary. So this can be used for identification of 1 degree amine. This is general equation, but if you take actual 1 degree amine like ethylamine, what you will get? You will get RNC. So here R group is ethyl isocyanide, and these are the byproducts. Next reaction, Hoffman mustard oil reaction. Why we call it mustard oil? Because in this case, the product that will be produced, that has specific smell which is just like mustard oil. So that is why the name Hoffman mustard oil reaction. Sometimes it is simply mentioned mustard oil reaction. This is also for primary amine. So what we do, we take primary amine. Now it is treated with carbon disulfide, CH2. Remember the formula of carbon dioxide, CO2. It is just like CO2, but now instead of oxygen, you have sulfur, it is CH2. N-alkyl dithiocarbomic acid is formed, which is treated with HgCl2. And finally, you get something which is having same smell just like mustard oil. So what primary amine we have taken? We have taken ethyl NH2, ethylamine. This is CH2. So it is capital S. First, what we are getting? Suppose if this N is attacking carbon, there is negative charge over sulfur, any sulfur, and that negative charge can take this H. So finally, what you are getting? ETNH C double bond S SH. Now, if you treat it, subsequent treatment with HgCl2, now what we are getting? We are getting ethyl isothiocyanate, C2H5 NCS, and here we have two sulfur, but NCS, as if this part is only remained after treatment with HgCl2. So markedly it has taken one S and it is forming HgS. And this ethyl isothiocyanate, this is actually ethyl isothiocyanate because the R group is, we have taken ethyl, but in general what should be the name? Alkyl isothiocyanate. So alkyl isothiocyanate is having, this group may be any alkyl group, pungent smell just like mustard oil, and that is why we call this reaction Hoffman mustard oil reaction. And this test also you can use just like carbonyl reaction, you can use it for identification purpose of primary amine. Though among these two, preferred method is the first one, that is carbylamine. So after finishing the different chemical reactions of amines, now we will try to understand the difference, that is how you can distinguish these three types of amines. Suppose you have some sample, you do not know whether it is 1 degree, 2 degree or 3 degree, but you want to know whether it is which type it is, then you can do this reaction, and it is known as Hinsberg reaction. Now what amine we have taken? We have taken this general structure R1NH2, this is 1 degree, then R1 R2H, only one H, this is 2 degree, and in this case we do not have any H, that is why it is 3 degree. But the reagent is common. Look at the reagent, it is PHSO2Cl. If you write the detailed structure, it will be like this: benzene ring, then S, 2 double bond O, then Cl. PHSO2Cl. So PHSO2Cl is the common reagent that we are using in Hinsberg reaction. When it is 1 degree amine, so as if this lone pair, it has attacked here, that is sulfur, and Cl is removed, which is good leaving group. So now you are having R1NH. One H is also removed, as if it is removal of HCl. This H and this Cl together removed, and you are getting something like this R1NH. This H is basically acidic in nature because it is attached to nitrogen, and then SO2 So this AnSO2, this total part is very electronegative. So that is why this H is acidic. Now as this hydrogen is acidic, it will be removed in presence of some basic solution. So now it is negative charge over nitrogen, and sodium plus is the counter ion, and as it is salt like structure, negative positive, so this is water salt. So this H can be neutralized by base. When it is 2°, there is no such hydrogen, and this is insoluble solid. Okay, so now the observation is different. In the previous case, not just that is, you can further continue the reaction. If you are adding NaOH and you are getting some salt which is water soluble, it proves it is 1°. But if you are in the first step, that is before addition of NaOH, if you are getting insoluble solid along with HCl, that means it is 2°, and in case of 3°, there is actually no reaction. So this PHSO2Cl, which is, the name is benzene sulfonyl chloride or phenyl sulfonyl chloride. This is actually Hinsberg reagent. Because we are using this reagent in this Hinsberg reaction, it reacts with primary and secondary amine and it forms sulfonamide. So this molecule is actually sulfonamide. Remember, amide. So in amide, what we have? NHCO. But here we do not have any CO, rather we have that is H double bond O. So that is why now name is different. Sulfonamide. Though nowadays this reagent is replaced by some other reagent which is para-toluene sulfonyl chloride. So it is actually same, that is again benzene ring SO2Cl. That is the reagent used in older days, but now it is para-toluene sulfonyl chloride. Okay. So toluene is having structure CH3 group at para position. So that is why it will be like this. Fine. Now we will also see separation. So it is not just that you are identifying some unknown sample of amine, but you can also separate them by using this method. So if you have mixture of 1°, 2°, and 3° amine. Mixture means you have 1°, then 2°, 3° all, and you want to separate them. So this is separation. That also you can do by Hinsberg reaction. So this property of amine towards PHSO2Cl, which is Hinsberg reagent, in different manner, this fact you can utilize to distinguish, not just to distinguish, because how you can do it for distinguishing purpose, that you have already seen, but you can also do it for separation of mixture of amines. So treating a mixture of 3 amines, I mean 3 different types of amines with this reagent, finally treating the product with NaOH, you can separate it. Now we will see in detail. So first there is mixture. So what you will do, you will treat it with PHSO2Cl. Now in case of 3°, there will be no reaction, but in 1° and 2° there will be reaction, that you have seen in the last slide. Now in 1°, there is still some acidic hydrogen present which can be removed by NaOH. So that is why it is salt and it is water soluble. So finally what we are seeing, if after treatment with PHSO2Cl, whatever mixture you have, if you treat it, that is if we do it some separation by extraction method. So extraction method means we take this type of separating funnel where there is water part as well as organic part. Organic layer means it can be any organic solvent. Mostly ether we take it. So when you shake ether and water layer together along with this reaction mixture, organic layer, that is ether layer, which that will be above the surface of water layer, and it will contain this 2° amine and that is the compound which is formed from 2° amine. I am not saying directly we will have 2° amine. The compound which you are getting by reaction between 2° amine and PHSO2Cl, that will remain in ether part, and also the unreacted 3°, that will also remain in ether part, and in aqueous part you will have the salt. Remember, the product that you get from 1°, that is the product by treatment of PHSO2Cl, that product Remember this structure. This product we treat it with NaOH, so now it is salt which is water soluble. So it will remain in the water layer. Okay. So if it is present in water layer, now two layers, normally we shake it vigorously, and if we, after shaking, if you keep it for long time, now what will happen? There will be layer separation, because ether and water, they do not mix to each other. So from this lower part there is a stopcock. You can remove this water part. So now water part and ether part both are separated. So in ether part you have 2 degree, that is a product that you get from 2 degree, and original 3 degree, and in this case the salt which is from 1 degree, that is present. So this water part, if you remove the water evaporation, if you do, then you will be end up with the one thing, it is in salt form, that means it is in sodium salt form. So you have to do some acidification, and finally the sodium ion will be removed, and you have to do some hydrolysis, because you want to separate the amine. So from this product, that is, this is your salt, if you treat it with acid, it will be converted to from N minus Na plus to NH. Then you have to do some hydrolysis. Finally this bond will be broken, you will get back the original amine. Okay, so in this way 1 degree is separated. Now once 1 degree is separated, you are left with this ether part which is containing 2 degree and 3 degree amine. So we have to do distillation. So here we have mixture of 2 degree and 3 degree, I mean the product of 2 degree and original 3 degree. So 3 degree, that will come in the distillate. Distillate, it is stored in the receiving flux. So in distillation what we do, we take some liquid mixture and heat is provided, and there is a condenser. So the vapor that is generated, that will come to this, and some cold water is running from this side, though the complete picture is not there. So this part, the vapor will be condensed, that is why the name is condenser. It will be converted back to liquid. Now as 2 degree is, there is some reaction with PHSO2Cl, but 3 degree it is still unreacted. So this 3 degree amine which is liquid, that will be stored in the receiving flux, and this is called distillate. And whatever amount is left here, that is the residue. So as if this is the before the distillation process, green color, and now it is containing the residue which is the product of 2 degree, and this is 3 degree amine. So 3 degree amine, it will be coming in the right hand side part, that is receiving flux. So 3 degree amine you have already obtained in pure form, and you are left now with the product of 2 degree, which is sulfonamide. So you have to break the NHSO2 bond, and for that you can do some hydrolysis in basic condition, and finally you will be getting back the 2 degree. Though there are some ether present that you can easily remove by providing heat. Ether boiling point is very low, it can be easily removed. Okay, so in this way we can separate primary, secondary and tertiary amines by using Hinsberg method. So this is one method. Another method is also there, which is Hoffman's method. Now in this case, these three together, that is 1 degree, 2 degree, 3 degree. Now we will treat it with ethyl oxalate. What is ethyl oxalate? First try to understand the structure of oxalic acid. This is oxalic acid. So when I am saying ethyl oxalate, that means these two H will be replaced by ethyl 2. Now, sorry, not just replaced, I am trying to say that is, it will be some ester, that is ethyl ester of oxalic acid. Now this mixture of 3 amines is heated with diethyl oxalate. Actually it is diethyl. So this reagent we actually use. In the previous method we have used PHSO2Cl, now we are using diethyl oxalate. Now different types of observation you can get when it is 1 degree amine. See, this is 1 degree amine, this is another 1 degree amine, and this is diethyl oxalate, ethyl ester of oxalic acid. Now if you look at this dotted region, as if this OET group and H is removed, that means 2 ethanol will be removed, and this CO, now it is connected with R in each R. So this is crystalline solid. You can call it dialkyl oxamide because this is also amide. See, CONH group is present, but the amide is 2 times connected to each other. So that is why dialkyl oxamide. So this is the product you are getting from 1 degree. Primary amines, they form solid oxamide. Secondary amine forms liquid oxamic ester. So see, even if you properly do not characterize the product, then also just by looking at the reaction mixture, if you are getting solid, then it is 1 degree amine. Because if you do not know what is the starting amine, what is its nature, but if you are getting the product solid, that means it is 1 degree. If you are getting product liquid, then it is 2 degree amine. And 3 degree amine, there is no reaction. So see, this is 2 degree amine we have taken, and only this is 1:1. The previous one is 1:2, but now it is 1:1 reaction. And this part there is no change, but now this part only 1 ethanol is removed, and you are getting dialkyl oxamic ester. And this is oily type of liquid. So this type of observation, one is solid, another one is liquid. We can easily understand that yes, this is 2 degree or 1 degree or 3 degree, because in 3 degree there is no such reaction. So after doing this reaction, now we are left with diethyl oxalate, which is the starting reagent and mixture of amine. So after reaction, if it is 1 degree amine, there will be solid crystalline, then oily liquid, and no reaction. But we have mixture, that is all these 3 amines we are trying to separate. That means all of them will be present together. Now as it is solid, these 2 are liquid because amine, this is originally liquid. If you do filtration in the residue, there will be 1 degree amine, and this 1 degree amine, as it is in amide form, if you do hydrolysis in presence of basic condition, you can get back 1 degree amine. So what will happen now? This bond will be broken and you will get 2 amine as free pure amine. But in the filtrate part, that is the remaining mixture, if you do fractional distillation, remember in the last slide also we have already seen how we are doing fractional distillation. So by fractional distillation, in the distillate part, there will be 3 degree amine, and the residue part, that is which will be remaining in the flask where from you have started the distillation. Now this residue part, that will contain this oily liquid, and if you do treat it with KOH, that is hydrolysis, if you do, then this part will be broken, amide will be broken, you will get back this R2NH 2 degree amine, and 3 degree amine already separated as distillate, that is pure 3 degree amine. So these are the two methods by which we can separate, not just I'm talking about distinguish, you can actually separate if all these 3 amines are present together. So now after finishing aliphatic amines, we have seen its preparation method, physical properties, chemical reactions, basic strength, their order. Now it is aromatic amine. So in aromatic amine also same thing we have to do, that is how we can prepare it, then its basic nature, basic strength. You can also compare the basic strength between aliphatic amine and aromatic amine, and finally what type of chemical reaction you can expect from aromatic amine. So in this table you can compare aromatic amine and aliphatic amine. So aliphatic amine, this is a 1 degree, actually all the first 3 1 degree, but remember no aromatic ring is directly attached to N. Don't think this is aromatic, because here pH ring is not directly attached to N, it is attached through CH2, and this is 2D. But if you look at the right hand side, now benzene ring is directly attached to N. This is the simplest aromatic amine possible, and it has common name aniline. Then 1 naphthyl amine, because this part is naphthalene. and you have NH2 at one position, that is why the name 1-naphthylamine. Similarly, this is position 1, this is position 2, it will be 2-naphthylamine. Sometimes it is called alpha-naphthylamine, this is called beta-naphthylamine. Fine. So aliphatic amine means nitrogen will be bonded to only alkyl group, but aromatic amine means it will be bonded to one or more alkyl group. So in this case, you are seeing 3 examples of aromatic amine, all are 1 degree, but not necessarily it will be 1 degree, it may be 2 degree also. Suppose there is pH ring, then N, H, but I am not writing another H, there may be any alkyl group. So this is also 2 example of 2 degree aromatic amine, because aromatic ring is directly attached. And there is another category which also you should know, heterocyclic amine. Now this amine in which nitrogen is one of the atoms of a ring. So heterocyclic, that means there will be some ring structure, and in the ring structure it is not that all the atoms are carbon. One carbon or more than one carbon may be replaced by some heteroatom. Now when I am saying heteroatom, basically I am trying to say it may be nitrogen, it may be oxygen, it may be sulfur. Mainly these are the elements that are present. So one of the carbon will be missing, there will be N. Not one, it may be more than one. Now see, these are some examples. This is called pyrrolidine. So here we have 5-membered ring, but not 5 carbons are present. One of the carbon is now replaced by N, and N is trivalent, so one NH bond is there. Similarly, if it is 6-membered ring, it is called piperidine. Now these two are example of heterocyclic but aliphatic. They are not aromatic. But the next two, they are also heterocyclic, because now also you have the similar type of 5-membered ring, 6-membered ring, but they are aromatic. But it is not that same thing. Benzene ring is not attached. There is no such benzene ring, but still why they are aromatic? So you just have to follow whether it is following 4n plus 2 pi electron rule or not. Right? Now if you look at the structure of pyrrole, there are 2 double bonds. That means 4 pi electrons are there. Now these 2 electrons also take part in resonance with these double bonds, and that is why the resonance structure will be like this. It is taking part. Now it is positive. So in this way, these 2 electrons, they are also, that is adding to this 4 electron. Now it becomes 6 pi. So it is also aromatic. Similarly, if you look at pyridine, though it looks like benzene, but one of the carbon is replaced by N. Just forget about N. Focus on these 3 double bonds. That means 6 pi electron, this condition is again fulfilled. But here lone pair of nitrogen is not part of the aromaticity, unlike the previous case. That is, in case of pyrrole, this lone pair is part of aromaticity, but now it is not part of aromaticity. So here you can say this lone pair is, its availability is more compared to the lone pair of pyrrole. That is the first compound. So these 2 are examples of heterocyclic aromatic amines. Fine. So heterocyclic, it may be both aliphatic as well as aromatic. Here we have one example so that you can compare. So just look at the structure of aniline. We are calling it aromatic amine because this ring, because of the 6 pi electron, it is aromatic. But if you just simply remove these double bonds, now you are left with cyclohexane ring where no double bonds are present. So cyclohexylamine, this will be, don't think this is aromatic, this is now aliphatic category. Structure of aromatic amines. In case of aliphatic amines, we have seen, if I write it like RNH2, it will be R2NH also. Here the nitrogen is sp3 hybridized, but unlike aliphatic, when you have aromatic amine, now there is something different. Before going to actual discussion, let's try to understand what is pyramidal inversion. Here you can see R prime, R double prime, R. So as if 3 different R groups are attached to N. But if N is sp2 hybridized, that means tetrahedral geometry should be there. That means the 4th position, there will be lone pair. But this is sp2. Now look at the right hand side extreme. as if there is some inversion when you are moving from this to this. Now the lone pair is downward. Now this is also sp3, but when you are moving from position, suppose this is position 1, this is position 2. When you are moving from 1 to 2, you have to go via this species. Now this species is sp2. See, here nitrogen, which is here, it is having planar arrangement. So all the 3 R groups, they are in the same plane and the lone pair is perpendicular to it. So this is as if a plane. And now it is sp2 hybridized. So when it is moving from 1 to 2, it is going via sp2. So sp2 hybridization is also possible, but remember, now the angle we know it is trigonal planar according to the hybridization of sp2. So in case of aromatic amines, basically sp2 hybridization is observed. So this inversion include a change of hybridization in which N becomes sp2 rather than sp3. But ultimately it becomes sp3. So this type of inversion is generally observed in aliphatic amines. But why we are discussing it? We are discussing it because just to make you understand that sp2 hybridization is also possible. So it turns into planar and the lone pair of electrons, now it enters p orbital. So when it is sp3 hybridized, there are total 4 sp3. 3 sp3 nitrogen will use for bond formation with these 3 R groups or maybe hydrogen, and the 4th sp3 that will contain this lone pair. But when it is sp2, there are actually 3 sp2 total. All these 3 sp2 will be used for bond formation with 3 R groups and 1 p which is not part of hybridization, that is unhybridized, pure p orbital, that will contain this lone pair. Okay, so this is the difference in structure. So trigonal planar or sp2 hybridized, the inversion barrier is 0. That means if it is already sp2 hybridized, there is no question of inversion barrier. And if it is sp3 hybridized, now it will go through sp2, then another type of sp3 is possible. Now there is some inversion barrier which is having some value 4 to 5 kilocalorie per mole. Now when it is aniline, that is the simplest aromatic structure, aromatic amine structure possible, this barrier is very, very low, somewhere around 1 to 2 kilocalorie per mole. And it proves that when you have aromatic amine, aniline, the nitrogen, it is not exactly planar. So don't think it is purely sp2 hybridized, because here also inversion is possible. And the ease of inversion is better. I mean, if you compare inversion in case of aliphatic amine, there is 4 to 5 kilocalorie inversion barrier energy required. In aniline, this inversion barrier is low. That means the chance it will remain in sp2, that chance is now increased. So in case of aromatic amine, if I ask that what is the hybridization, it is not exactly sp2, it is not exactly sp3, but it is something close to sp2. Fine. So this is the structure of aniline. Here double bonds are not drawn. Instead, you can see this p orbital containing lone pairs. So all these carbons we know in benzene ring they are sp2 hybridized, and carbon uses 3 sp2 for bond formation with these 3 sigma bond, and the pure p that contains this lone electron, which is basically forming this type of pi bond and resonance. And this NH2, if you see, this is an unhybridized p orbital, and as if nitrogen is sp2 hybridized. So it is more close to sp2, so that's why we are saying it is sp2 hybridized. Now the question may arise, why it is so different? Why it is not purely sp3? Why it is close to sp2, unlike aliphatic? Now remember, in aliphatic amine, there is no such resonance possible. But when it is aromatic amine, the lone pair that is present over nitrogen, that can take part in resonance. So as it is taking part in resonance, the important condition for resonance is that planarity must be present. So this is the driving force. Why it is trying to achieve planarity? And planarity can be achieved only when it is close to sp2 hybridized. Otherwise, how planarity will be achieved? And only when planarity is achieved, then only resonance is possible. So that is why their hybridization is to some extent different. It is not exactly like aliphatic amines. So nitrogen almost has a planar structure. In case of aromatic amine, you can consider the simplest one, which is aniline, and CN bond length is shorter. Now why CN bond length is shorter? It is because of the resonance. Because when there is resonance, I mean the lone pair of nitrogen is taking part, it is undergoing resonance with the double bonds of benzene ring. Now there is double bond formation between carbon and nitrogen. So that is why now the bond length is shorter. So if you simply consider this CN bond length in normal aliphatic amine, and if you compare the CN bond length, I mean I am talking about this bond because there will be some double bond character. There will be interaction between these two p orbital, and that is why because of this double bond character now the bond length is shorter, because double bonds are always shorter compared to single bond. Basicity of aromatic amines. So look at this resonance structure as I have said. So suppose this is the first structure possible. Now the lone pair is interacting with the double bonds. It is now positive, this is negative. Suppose this is structure number 1, this is 2, but negative charge is present at ortho position compared to NH2. Then the next possibility, now it is present at para position or position number 4. Structure number 4, now the negative charge is present at another ortho. And then finally, the negative charge and positive charge is removed. You are getting another arrangement of benzene ring. See, here the position of double bonds in the first structure and the position of double bonds in the last structure, it is alternating. So in aniline or any other aryl amine, suppose naphthylamine, this NH2 group is attached directly to benzene ring. Now, because of this direct attachment, the unshared electron pair, that is a lone pair of a nitrogen, that will be delocalized into the benzene ring, and thus as these electrons are doing some other job, so they are no longer available. So in presence of acid, this lone pair cannot be donated to the proton, so it is less available for protonation. That means basicity compared to aliphatic amine is decreased, because in aliphatic amine no resonance is there, double bonds are lone pair is still available, but in this case lone pair availability is less. But if you consider anilinium ion, this molecule is aniline, but what is anilinium ion? Suppose aniline, when it is protonated, now it will be something like this, NH3 plus, and when it is anilinium ion, now you can have maximum 2 resonating structure, and these 2 resonating structure is basically, there is no change in this part, only change is in the benzene ring. Look at the position of double bond, they are alternating. So that is the maximum 2 resonance structure you can get, and it has nothing to do with NH3 because lone pair is no longer available. How it will engage in resonance with the double bonds of benzene? Fine. So only change that is in the benzene ring in the position of the double bonds. So when it is anilinium ion, maximum 2 resonating structures you can get. So this is the reason that aromatic amines are less basic compared to aliphatic amines, and also ammonia, NH3. So if you look at the pKb values, pKb value means, we have already discussed it, when pKb value is very high, that means basicity is low, inverse. If you consider directly Kb value, then it is directly related, and pKb and basicity, it will be inverse related. So among all these, if you look at the values, this is highest among all these values, 9.4. That means aniline, this is least basic among all these molecules. Sorry, not 9.4. Sorry, this one. This is least basic, and the reason is NO2 group, which is having minus R effect. Because of the minus R effect, now the lone pair availability, it is even lesser. That is, just compare these two. In aniline, you do not have any other group. It is 9.4. But when you have electron withdrawing group, now lone pair availability is further reduced. So now the pKb value is 13. Similarly, if you have any plus R group, donating group and remember this is applicable only when that is plus R effect or minus R effect, that is applicable only when it is at ortho and para position. So here we have para substitution. So when it is plus R effect, now it is 8.7, which is greater than lesser than 9.4. That means para methoxy aniline is more basic compared to aniline. So when it is nitro substituted aniline, this type of resonance is possible. If I write nitrogen, that is NO2, this is the actual structure, then NH2. So in normal aniline, there is no group at 4 position which is drawing the electron, but now there is some group which can draw this electron. So the new resonance structure that you are getting, this is positive, there is negative charge over oxygen. So because of this electron withdrawing group, now this lone pair over nitrogen, its availability is further reduced, and that is why it is least basic among all these. But the first 4 examples, they are aliphatic amines, right? So we have ammonia, then we have 1 degree amine, 2 degree amine, 3 degree amine. So see, 1 degree amine is more basic compared to ammonia because there is some plus I effect. Then 2 degree 3.3 is almost same. Then 4.3 3 degree amine, again it is basicity reduced. Now only aliphatic amines, how the pKb value, that is basicity changes, that is already discussed separately. So if you want to know why they are changing like this, you can consider the discussion. But if you in general consider, that is aromatic amine and aliphatic amine, obviously aromatic amines, because of this resonance, lone pair availability is very less, and when lone pair availability is very less, then how it will show basicity, right? So what are the factors that affects the basicity of aromatic amines? Now we are solely focusing on aromatic amines because we already know it is less basic than aliphatic amines. But that is, if you have 4 to 5 aromatic amines, how you will compare, that we can understand here. If you have electron with donating groups such as methyl, methoxy, NH2, that is another NH2 group. Suppose in aniline there is another NH2. So this type of groups, they will increase basicity. But if it is electron withdrawing group like NO2C, NCSO3H, any halogen, then obviously basicity will decrease. Overall basicity for ortho, meta and para substituted aniline, that depends on 2 factors, that is the combined effect of electron donating, electron withdrawing resonance, and also inductive effect. So when you consider minus R effect, which is possible only in some groups, that is NO2 group, it is possible, or plus R effect. So these 2 effects possible only it is at 2 position and 4 position. But plus I effect or minus I effect, that can be applicable at any position, because inductive effect, there is no such thing that it has to be at 2 and 4. But it is also true that inductive effect decreases with distance. So when the group which is showing positive inductive effect, if it is present at ortho, obviously it will have more positive inductive effect rather than meta and para, because distance is increasing. So when you will consider the overall effect, you have to take, it is a combination of electron donating, withdrawing resonance. That is resonance you have to consider minus R or minus R or plus R, as well as you have to consider whether there is plus I effect or minus I effect. That also you have to consider. Here we have example. See, this is para-methoxyaniline, but as it has plus R effect, you can also say that OME, it has minus I effect. But remember, though it has minus I effect, but R effect is always more important than I effect. So that is why ultimately R effect will win over I effect. So here we are considering this plus R, this lone pair is donated, and as a result, now electron availability at this position is increased, which will further increase the electron availability over nitrogen. So it is more basic now. So this is para-methoxyaniline, stronger base compared to when there is no substitution. Now come to the right hand side. When there is CHO group, which is electron withdrawing group, you can consider same type of resonance as we have seen in the last slide. That is at 4 position, remember? The NO2 group. Now we have CHO group, which is electron withdrawing group. How it will show electron withdrawing capacity? So see, in this way it is possible. Now nitrogen is positive, so it cannot give lone pair. It is already engaged. So in this way, when it is electron withdrawing group, it is becoming weaker base compared to NH2, that is aniline. But if there is OMe group like donating group, it is becoming stronger base. Here we have different order. I mean, the first one is chloro substitution. Now it may be at para position, meta position, ortho position. Then we have NO2 substitution. This may be meta position, para position, ortho position. Okay. And then we have methyl group, methyl substitution. Now this is para, then meta, then normal aniline, and then ortho. So these are the order for basicity. Look at the pK values, it will be reverse. So if it is maximum basic, that means this value will be minimum. Look at the values 9.38, 10, 11.52, 13.3. That means this aniline is most basic among all these three. The next two, it is NH2 substituted aniline. That means another NH2 group is there. So this is maximum, then meta, then there is no group, I mean aniline, and ortho. Then we have OCH, I mean methoxy. So this is para, ortho, meta. So it is the combined effect. If you simply consider only plus or minus, it will not work. If you really want to know what is the actual reason for this type of order, it is because of the combined effect. But one thing we have noticed that ortho substituted aniline, irrespective of the fact whether it is withdrawing or donating, it is observed that they are usually weaker bases compared to aniline. I mean when there is no substitution. So see, in the first case, aniline is here, this is ortho. Aniline is here, this is ortho. Aniline is here, this is ortho. So in always compared to aniline, the ortho one, it is less basic. Then in case of here also, aniline is greater, and here aniline is greater than ortho. So that is it is written aniline. It is observation. Remember, it is observation. Aniline, regardless of the nature of substitution, whether donating or withdrawing, it is always weaker basic, and that effect is known as ortho effect. And though it is not fully established fact, but probably it is because of combination of both steric effect and electronic factors. So how it can apply? That is electronic factors, that is related to minus R effect, plus R effect, or inductive effect. But steric effect means when any group, whether it is donating, withdrawing, if it is present at ortho position, obviously the site where this lone pair will be donated, whatever is the site where it will be donated, that cannot approach the aniline, ortho substituted aniline, so easily because of this steric problem. So that is why sometimes there is some hint. So that is it is written here. It is a combined effect of both steric as well as electronic. Okay. So some more factors related to aromatic amines, that is the chemical reaction, especially that part is left, that will discuss in the next class. We are ending the session here. Thank you for listening.